Hi, this is going to be the lecture on refraction. So let me define the term as I've written it down here. When a wave crosses from one medium to another, then it changes its speed. So, for example, if I have sound that goes from air into water, or light goes from vacuum into glass, or even, say, an ocean waves go from part of the ocean where it's deep to somewhere where it's more shallow. That'll also change the speed of it. Now, when you have a change in speed, this will result in a change in the direction of travel of the wave, and we'll see how that is. By this phenomenon, that a wave, and more often than not, we talk about light, but not exclusively, when a wave hits a boundary between two different media, it changes direction. Now, in addition to that, you also get, in such a case, you get a bit of reflection. You get some reflection, and I'll show that to you later. And in certain cases, you get something what's called total internal reflection. We'll talk about that too. But even when you just have, say, a laser beam passes into water, then some of it bounces off and gets reflected. Some of it goes in, which is, for example, why you can see reflections on water, right? But you can also see into the water. Alright, so let's explain this first. Let's explain why this sort of thing occurs. Let me draw a picture. Alright, so here is, here's where we were. Here's my picture. I imagine a bunch of lines of soldier, right? A Napoleon soldier. Here's Napoleon riding what I guess is a rat. I was trying to draw a horse, but it didn't go very well. So now Napoleon is riding a giant rat. And the lines of soldiers that he's commanding, they're marching along, and they're told, hold the line, and they're told to march perpendicular to the line, like the way you'd naturally imagine soldiers would march, unless doing some kind of fancy dance. So they're marching through Russia on a doomed mission, and they march across dry land, but then they hit this swamp, right? So here's a swamp. The medium changes. Now, how are those soldiers that are marching down, and they're going to be marching sort of this way, I suppose, right? How can they continue to obey the order to hold the line and march perpendicular to the line? And I guess another one should be, don't change your speed without good cause, or something like that. Just imagine they don't really look left or right, they just march along. They've been marching for 10 days straight. So they enter the swamp, and when they're in the swamp, they've got to march slower because it's a swamp, right? I hope that makes sense. But each one, right, stays, looks left and right, the guys to left, the guys to the right, to hold the line. Now, because they're slower, right, because they come in an angle, the person like on the bottom end of the line that we have drawn is going to hit the swamp first. They have to sort of fall behind, and the next person is going to hit the swamp and start falling behind. So you get that the line sort of changes like this, right? Just because that guy down at the corner got slowed down first, and the next guy got slowed down. And then if I draw the next sort of line, and you can imagine how those look like waves, it should be parallel, those two didn't draw this very well, it will look like this. The next one would look like this. And then the next one, I guess, is just like one guy who's still outside of the swamp, but the other ones have entered the swamp. And just by holding the line, staying in a line, not breaking the line, and marching perpendicular to the line, will the line change direction? My wavefront, as it were, is change direction because one end of it got slowed down before the next part. Like this person here got slowed down a long while ago, while this person here only gets slowed down just now. This person here got slowed down a long time ago, while this person here is only just now getting slowed, and all the stages in between. And so that is why this one was falling behind. It isn't like down here where they would be if there hadn't been swamp. But because they're told to march perpendicular to the line, this change of speed that one end experiences before the other means they're going to change direction as well. So up here they're still going this way, but this one over here is already changed direction, and then eventually all has changed direction. Right. Now, of course, those orders, maybe they wouldn't be the most natural, and if Napoleon has half a brain, he probably would do something about this. But hold the line, right? It's just saying, look, lines, their wavefronts, they continue to be wavefronts, right? The waves are continuous. March perpendicular to the line is something that waves obey no matter what, right? They move perpendicular to lines of constant phase, perpendicular to crests, perpendicular to troughs. But the effect is that if I draw this as a ray, right? That's kind of what I was trying to do here. The rays come in until they hit the or maybe it's multiple rays, right? Until plane wave rays come in until they hit the swamp, and then it changes just because of the way waves obey these sorts of commands. Right, and here as well, I guess I could do it like this, and then keeps going until it hits the edge, and then it goes down like this. And this one is not going down like this. Always perpendicular to wavefronts. So we get this change in the angle. So that's the intuitive explanation, why the waves change. And it's fairly accurate, right? Of course, it's not dry land and swamp, but it might be light moving in air, light moving in glass. Or if it's sound moves faster in water, so maybe sound moving in water, sound moving in air. Right? And there'll be a change in direction of the wave. Let's look at the geometry a little bit more. So here I sketched a close-up of the geometry. Again, I stuck with the same colors. The blue ones represent my rays, the green ones represent the wave crests. Now, a little mistake as I was drawing it, ignore this line here, right? Try to cross it out. The wavelength out here is longer, and then because of that refraction effect, the wavelength in here gets shorter. Right? It gets shorter, well, because of this sort of squeeze, because they're marching more slowly inside. So I want to relate those two angles. This is going to be called the angle of incidence and the angle of refraction. Right? They're different. They tend to be measured from the normal. I could measure the angles like from the surface, but the convention is to talk about the angles as measured from the normal, from the line that's perpendicular to the surface between the two media. Right, so angle incidence, angle of refraction. Let's label those. This is my angle of incidence. And this down there is going to be my angle of refraction. Alright, so I want to relate those two angles. Now, here's how we're going to do this. Let's identify the wavelengths outside and inside, right? So, out here, the wavelength is essentially distance from one wave crest to the next one. So, out here, I should maybe label it like this. This distance here, this is lambda in medium 1. Lambda 1. Right, from this wave crest to next wave crest. Down here, well, I guess I could pick this one here. Right, this would be lambda 2, which is shorter. The frequency is the same because the soldiers that march on, right? There's still the same number of soldiers that passes a point here is going to pass a point here every second. Just they're much slower, but they're also closer together. So you end up with the same. Like if you stand by the side of the road, you like the lieutenant or captain or whatever standing there watching the army go by, then you see as many soldiers passing you here as here every second, except here they're further apart but walking faster. The frequency is the same, but the wavelength gets squished. That is what changes the speed. Okay, so how can I relate all those quantities? So here's what we're going to do. This angle here, right, is whatever it is, this angle down here would be 90 minus that, and so that makes this angle here again theta 1. So what does that give me? It means I can express this length here between those 2 points, so those adjacent rays, the way I've drawn it, as L is equal to, this is the hypotenuse, so sine of this is wavelength, this distance here, over this. So I can write this as the length as lambda 1 divided by the sine of theta 1. Alright. Now down here, I can do a similar thing. This is the angle that I picked, but that means this angle here next to it is 90 minus this, because the rays are perpendicular to the wavefronts. That makes this angle here again theta 2. Right, and then looking at this triangle here, I've got the wavelength is from here to here, right, lambda 2, okay, I've drawn it here, but same distance here. Wavelength, lambda 2. So sine of theta 2 is wavelength over L, right? And so L is wavelength over sine of theta 2. So down here I can say L is lambda 2 over sine theta 2. Okay, so now, because the frequencies are the same, I can then re-express this in terms of the wave speeds. Right, I can say lambda over sine theta 1 is equal to lambda over sine theta 2. And if I multiply both by the frequency, which is the same, I get that v1, the speed up here over sine theta 1, is v2, the speed down here over sine theta 2. Let's write this out. See if I can show you what's still up here while we're working through it. So what I have right here from this observation is that lambda 1 over sine theta 1 is equal to lambda 2 over sine theta 2. And because the frequency is the same, it must be, otherwise I guess the waves just what build up here, like they queue up. No, of course the frequency is the same. So you can multiply both sides by the frequency with the same frequency, and so I get that v1 over sine theta 1 equals v2 over sine theta 2. Oops, you can't see this. There we are. Alright, so the speed over the sine of the incident angle is equal to the speed in the other one divided by the sine of that, the angle of refraction. Alright, now the next thing we tend to do in the context of refraction is to define what's called the index of refraction. And it's really defined for electromagnetic waves more than anything else. You could define it for other waves, but it's not usually done. So for electromagnetic waves, define what's called the index of refraction. And we give it the symbol n, and usually n, and then down here we put the medium, so n air, n water, and so on. And that is defined as the fraction of the like n times the speed of light in vacuum gives you, let me say this again. The speed of light in vacuum divided by n gives you the speed of light in the medium. So it makes n equal to c, the speed of light in vacuum, divided by the speed of light in the medium. Let me write it like this. there's no single way people write this. C normally means speed of light, and if it's not further specified, it's in vacuum. But here I've got C in the medium, and I get air or in water and so on. Now I could define the same thing for other quantities as long as I've got some kind of base value, right? But that's usually done. Now because this is bigger than any of the others, like light slows down in glass, in water, in diamond, anything it can travel through, this tends to be greater than 1. So greater equal 1. So 1 would be vacuum, glass is 1.5, so that means light goes 2/3 of the speed of light in vacuum and in glass, so about 200,000 kilometers a second rather than 300,000 kilometers a second. Water is about 1.3. Diamond can be something like 2.4, which means light is very slow, and so on. What does it depend on? What's the physical explanation? Why does light slow down? Well, light is electromagnetic waves, and when it falls through something that is made up of charges, such as any kind of material, it interacts with those charges. Now that process is fairly complicated to analyze mathematically. You can do it, and if you take some more advanced electromagnetism course, you will do it. And you can show that the final result is that light essentially travels more slowly. Right, so the electromagnetic fields interacting with the charges that are there, their wobble creates their own electromagnetic fields. The final result, after everything's said and done, is that light moves more slowly in a medium, depending on the particular properties of the material. The details don't concern us. We can sum this up by defining this index of refraction. And in practice, you'd determine that experimentally. Now, when I use that to put it in here, essentially what I'm going to get is that n1 sine theta 1 is equal to n2 sine theta 2. Right, so I plug, so v1, v2 would be essentially C in medium 1, C in medium 2. You plug those, you rearrange, you plug those in, you cancel out the vacuum, and you end up with this. Just make sure you can do this. So pause for a minute and just fill an intermediate step. This law is called Snell's law. I know very little about Snell, but it was discovered experimentally first. Like before we had any kind of theory of light, what is light? Is it a wave? Is it something else? Who knows? This was just observed experimentally, right? But we can justify it via that derivation by analyzing the geometry carefully here. Okay. Now, most applications of refraction really just use this as a starting point. So let's use it and do some examples. So here's example number 1. Light falls into a glass, and the index of refraction of glass is 1.5 from air, and the index of refraction of air is 1.0. The same as vacuum, sort of. It's really 1.000 something, so it's just above 1, but for all practical purposes, it's 1.0 to a very good approximation. At a 30 degrees angle of incidence. So what does that mean? Angle of incidence is if this is glass down here and here's air up here, this is my surface between the two media. Angle of incidence, remember, is this one here. So this is 30 degrees. How fast and in what direction does the light travel inside the glass? Question mark. Okay, so the speed, right, speed of light in glass is the speed of light in vacuum divided by the coefficient, so the index of refraction of glass. So the speed, to answer this one first, speed of light in glass is equal to c, the speed of light in vacuum, divided by the coefficient, index of refraction of glass. Right, so this is going to be equal to 300 3,000 kilometers per second, or 300 million meters per second, divided by 1.5. Notice that the index of refraction does not have units, right? Because it's a ratio of speeds, as it were. It just comes to 200,000 kilometers per second. Now, what does it look like? What path does it take? So one rule of thumb, I mean, it works always, it's a good rule, is that if a ray falls onto an interface between two media and the index of refraction is greater, it's gonna, in the medium that it goes into, it's gonna bend towards the normal. So it becomes, depicted as here, it would become steeper like this. Whereas when light goes the other way, it goes from a medium of high index of refraction, say from glass, into air, a medium of a lower index of refraction. It would bend away from the normal, like the normal always being the line that's perpendicular to the interface between the two media. Right, so, but what's this angle here? This is my angle of refraction. And if I state that, I've answered, which way does it go, in what direction does it go? Well, in this direction. And here I can use Snell's rule and Snell's law. Snell's law states that n air sine theta air is n glass sine theta glass, right? And of course, the angle of refraction is this theta glass. This is my theta air, and this is theta glass. Just a different way of denoting the same thing. Right. Okay, so I can plug in the values. Actually I can rearrange first because I want to find this angle here. So I get that sine of the angle that I want is equal to n air over n glass times the sine of the angle the ray makes in the air, this one here, like this. So that's 1.0 divided by 1.5 times sine of 30 degrees, and a 30 degrees is a half. This is 2/3, right? So half times 2/3 is 1/3. So it's 1/3. So therefore, the angle itself is the inverse sine, the arc sine of 1/3, and unless I'm mistaken, as my calculator fools me, that is about 19.5 degrees. And that completes our answer. This angle here, about 19.5 degrees, if this angle here is 30, and it's air and glass. Alright, let's do another one. Here's example number 2. The sun is about to set on the ocean, and the index of refraction of water is 1.33. Depends a little bit if it's salt water, is it non-salt water, is it, and what's the temperature. So always little variations, but it's a pretty good estimate. Where does the fish see the sun? So if the sun's essentially down here, now of course the sun isn't really just above the ocean, it's not sinking into the ocean, it's out in space, right? But it's in that direction. So the ray moves effectively parallel to the surface, right? The ray that hits the surface that the fish sees moves parallel to the surface, and it bends when it hits the surface. Of course, it's not exactly parallel, but it would never hit the surface, but it is fairly close. So I want to imagine it's essentially, for all practical purposes, parallel. Right, the ray goes like this, and then it hits the water, so it bends down, bends towards the normal, like we just said, and hits the fish. Right, so the normal in this case is of course here. Alright, so let's figure this one out. Well, where does the fish see the sun? The fish seems to see the sun right higher up in the sky, because if you're the fish and you look, the sun seems to be coming from this sort of angle here, because the fish doesn't know about refraction. So let's work this out. Well, let's find the relevant angles. So the Snell's law states that n, well, this is air and water, right? So n air sine theta air is equal to n water sine theta in the water. I want to find this one here. Okay, that's my goal. So we know those values, right? This is here, this one is 1.0 for practical purposes. This one is 1.33. Now what's the angle? Well, it's perfectly flat, so the angle between the ray and the surface is 0. Maybe it's 0.1, right? Doesn't matter. I mean, the sun it's not a point, it has an extension in the sky, so it's going to be a range depending what part of the sun you look at. So we're going to go with 0. But note that the angle is measured from the normal, so I have to make sure I take this angle here as the angle theta air. Alright, so that is going to be 90 degrees. Or 89.9, but doesn't matter, right? 90 for practical purposes. Well, then I can solve this for the sine theta water. You just do math, fairly straightforward. What you find is that everything said and done, the angle is going to be the inverse sine of 1 over 1.33. So sine of 90 is 1, right? This makes this whole thing 1. So I just get 1 over 1.33 being equal to sine. So another way of saying is the arc sine of 3/4. Again, make sure you can follow that. 1 over 1.33, roughly. Which comes to 48.6 degrees. All right, so this angle, which angle is it? Well, this angle here, right? So what's interesting is that the sun can't go any lower, right? Otherwise it won't be seen at all. So that means the fish is never going to see the sun below an angle like this. It's always either that high in the sky or higher. It is never down here somewhere. But the fish always thinks the sun is at least that high in the sky at that angle. We'll come back to that number in a little bit. Alright, so here's my next example, and this one is a little bit more involved. Imagine I've got a pool of water and the pool is 2 meters deep, that I've drawn here. How deep does it appear? So this is an effect that you notice when you go to a swimming pool, like you look down the water and the water doesn't seem to be as deep as it actually is. To figure this out, I imagine there's some object at the bottom, maybe a penny, right, that I'm looking at. So this is my point. I'm going to try to figure out how deep below the surface do I see this object. Now, if you want to see how deep, how far away an object is from you, you're going to need 2 eyes, right? So I'm going to imagine I'm going to look straight down from above. Now, to actually be able to draw this, I need to draw my eyes really far apart, otherwise it'll all be very cramped. So I'm going to imagine like an eye over here and an eye over here, right? It's not to scale, obviously, but it shows you the right idea. Let's draw some rays. Right. So first, let me draw this straight line up. This is of course also my normal that comes out of the surface of the water. Now, let's suppose I do the following. There's some ray that goes this way. Of course, the rays go in all directions, right? But I'm just going to draw the ray that happens to hit my eye. Now it bends like this because it's coming out of the water. Right? And I imagine my eye is up here. This is my one eye. Now to make my life simpler, my other eye might be right above it. If I'm looking right down, the penny, the light is not going to bend at all. This is this ray that hits the surface straight. It's just going to keep going. So imagine those are my 2 eyes. Further apart than in real life, but drawing it this way makes the geometry manageable. So where do I see an object? I see an object in a place where the rays from my two eyes, like where the rays meet, right? The rays that reach each of my eyes where they meet, that's my brain thinks that the object is. So let me draw this. So here I'm going to extend this line right this way here. Because my brain thinks, yes, it knows about refraction in, theory, in physics courses, it doesn't interpret automatically refraction correctly. So my brain thinks that the object is here, this is down here is the actual object, whereas this here is what we call the image of the object. Right, that's where my brain thinks the light is coming from, because my brain doesn't know that the light actually changed direction at the surface. So now we're going to do a little bit of geometry. So this is where the ray hits the leaves the water. So I'm going to draw my normal right here, like this. Right, and then of course the two relevant angles I'm going to consider are this one here, the angle in the water, and then the angle outside, and that is the angle right here. Right, so this would be my angle of incidence. This time that's the angle in the water, and then this would be my angle of refraction. Now, if you look at this angle here is the same as this angle here. Let me call this, give those angle names. I'm going to call this, let's not call it theta every time, let's call it beta, right? It's angle beta. This angle down here is going to be alpha, and of course this alpha is the same as this angle here, just because it's a single line and those two lines are parallel. Okay. So now what I'm going to do is I'm going to look at two triangles. I'm going to look at this triangle up here. Let me call this distance here. It doesn't matter what I call it. Let me call it L. So kind of length, right? Well, what I want to know, right, is what is this height here? This is the apparent depth. I'm going to call this S prime. Whereas this here, this actual depth, I'm going to call S. That's just a common notation we use. That the primed one, like the same quantity prime, the sort of apostrophe, is the image quantity, right? The real thing is S. It's a real depth, but the image appears to be a certain depth down. That's what my brain thinks it is. That's S prime. So I want to find this quantity. I'm going to look at two triangles. I'm going to look at this little triangle here, like this, and I'm going to look at the big triangle with alpha. So in the little triangle with the red angle, what do I have? I have, let's have a look. This is the right angle up here, so I can write that, can't see this, here we go. Tan beta is opposite over adjacent. So that's L over S prime. So that is that little triangle up here. Let me draw it like this, so you remember what it is. With this being the angle beta. That's where we got it from. And then the other angle down here, right, this is going to form this big long triangle here. It also shares the side L. Draw it like this. Right, the tan of alpha is equal to L over the real S, opposite over adjacent to this angle. L over S. Right. Now I can put those two together, eliminate L between them, and I find that S prime is equal to S times, did I do this right? Let me check, so I'm not telling any nonsense. So S prime is L over tan beta, but L is S tan alpha, so it's tan alpha over tan beta. Alright. So I don't know what tan alpha over tan beta is, but what I do know is that sine, so let me write but, right? Sine alpha over sine beta is equal to the ratio of the indices of refraction by Snell's law, right? So this is going to be n, let me get this the right way around. So alpha is the angle down here, so it's going to be sine alpha times n of water is sine beta times n of air. It's going to be sine air, sorry, n water over, n air over n water, right, by Snell's law. And now I'm going to cheat, as always. I'm going to use the small angle approximation. I'm going to say then that sine alpha is approximately tan alpha, and approximately alpha as well. Same for beta. Sine beta is approximately the tan of beta. Why am I justified in doing this? Well, because if you actually imagine how far my eyes are apart, right, they'll be really close together. I can't draw it that way. All this stuff in here will be very squished. But my eye, if this is 2 meters, I put one eye here and one eye right next to it. Right, and my brain can deal with those small angles and discern where the object is, or at least where it appears to be. Of course, I had to draw them further apart to be able to show you the angles. But really, I should have drawn this eye really, really close here, or maybe this one next to there. Either way, right, the angles will be small. The angles between those two rays would be very, very small. So I'm justified in doing that. So write this down, small angle approximation. You know what you're thinking. You're thinking this course is really a course on various application of small angle approximations, and you wouldn't be wrong, right? It is a theme that appears to creep up again and again. Alright, so now we can put the pieces together. I can this is equal to this, which is equal to this, and so I get that S prime is equal to S times the index of refraction of air divided by the index of refraction of water. Let's work this out for the actual values we have. That's 2 meters times 1.0 over 1.33, right, water. And so that comes to about 1.5 meters. So the pool only appears to be 1.5 meters deep, as opposed to 2 meters, which it actually is. Now, of course, I've drawn this greatly exaggerated here. This idea of finding an image of an object is going to come, we're going to come back to that again and again over the next couple of days, or next week or so. Alright, so those were 3 examples. Let's talk about a couple more aspects related to refraction. Okay, so remember the fish watching the sunset? So we figured the fish is never going to see the sun below some angle in the 48 degrees or so in the sky, right? Because when the sun is right down here, that's when the fish would see the sun sort of up here, because that is the angle by which light refracts when it falls on the water extremely shallow, at a shallow angle. Now, let's imagine our fish has a laser. When you say fishes don't have lasers, and I say, well, you haven't seen the US government. Anyway, let's imagine our fish has a laser. Now, if our fish shoots a laser, right, the laser will essentially follow the same path as the light ray coming in, except in the opposite direction. Now we can prove that like Snell's law, in a sense, works both ways, right? So if our fish, say, shot a laser upwards like this, say from here, maybe our fish's laser eyes, right? It shoots a laser like this, then this is the normal. It'll bend and do something like this, maybe. Right. So this is just in this case angle of incidence times index of refraction of water is angle of refraction, the one out here, times the index of refraction of the air. So should have labeled this. Down here is the water, up here is the air. I think it was pretty obvious. Now our fish could decide to shoot at the laser at that angle that corresponds to the one where the sun was really low here. So let's do that. Fish might do something like this. So I'm not drawing it exactly, I'm not measuring my angles. And then the laser beam will go exactly along the surface of the water, just outside it, maybe 0.001 degree above. And the angles here are the same angles that we calculated earlier. Right, and we said, well, the fish will never see the sun below this angle here, like below this angle here. The sun will always appear to be at least up here or higher up, because the sun can't go below the horizon. But our fish can choose to shoot the laser at an angle more shallow than this. So what happens then? If I want to change my laser color to red, doesn't really make much difference. Let's imagine our fish shoots the laser in this direction. So what happens now? There is no angle there's no angle of refraction here that matches this one. Let's do that mathematically, right? So this is my normal. I'm going to suppose that this angle here is let's make it 60 degrees. Right, so bigger than the 48.6 or whatever it was that we calculated for this one here, and correspond to the light being essentially horizontal outside of the water. So what happens now? Well, let's look at the math first. So what Snell's law says is that n water times sine of 60 degrees is n of air times sine of, well, the angle outside, the angle of refraction, in this case the angle it makes in the air. So let's solve this, right? So sine of 60 is 0.86 thereabouts, and this is 1.33. It's equal to 1.0 times, what? My unknown here, times sine of, this is some value. Now, of course, this is 1.33 times 0.68. I don't know what it is, but I can ask a calculator. And if I'm not mistaken, it comes to about 1.144. So this implies that sine of theta air is equal to 1.144. Okay, now do you see a problem here? Because I do see a problem here. The problem is that the sine of an angle is always between 0 and 1. So that equation here, that result we come to, just isn't true. There is no value that makes that true. So theta air does not exist. It only works because we're going from a medium that has higher index of refraction, this, to a medium of a lower index of refraction. Like that way, this thing here, or more precisely this thing divided by this thing, can be bigger than 1. Right, and so that's how we get ourselves into trouble. Now before, even in like normal refraction, when we didn't have this strange situation, there was always some light that got reflected, right? So, hard for me to draw with all those diagrams or all those rays already there, but there's always a little bit of light that gets reflected like this. A little bit of light that would get reflected like this. It's reflected on the surface. And the same is true when light comes in from above. Some of it gets reflected, right? You can see reflection in water, even though some light also gets into the water. Now what we get here is what's called total internal reflection. So no refraction, the light does not, the wave, I'm going to write light, but it has other waves too, does not leave the medium. It has the higher index of refraction, higher value of n. Instead we get what's called total internal to the medium, in this case internal to the water, total internal reflection. Okay, so what is the, like 60 degrees total internal reflection, but we could go a bit lower, right? What's the sort of condition that there is total internal reflection? So, we sort of come back to this equation here, right? If we don't have sine 60, but sine of some other angle, well, what angle would I need to put in here? What angle would the fish need to choose for his laser, so that this equation comes out to be unsolvable in the way it was here? Well, let's have a look. So I can write in general n1 sine theta 1 equals n2 sine theta 2, right? So Snell's law, 2 media, 1 and 2. So we want there to be no solution for theta 2. So total internal reflection, total int reffel, right? If sine theta 2 is greater than 1, because then there's no answer, right? There's no angle that makes it true. So i.e. n1 over n2 sine theta 1 needs to be greater than 1. And so that value where, so those two are just given, right? But that value of angle of shooting from below, in our case it was 60, right? But 60 was, gave us 1.144. It's well above 1. The angle where we just barely have bigger than 1, or just at the boundary where this is equal to 1, that's what we call the critical angle. The critical angle, if dirt there, ignore that. Theta crit is going to be when this is exactly equal to 1. Like that's the maximum angle the fish could pick, the maximal like shallowness that the fish could pick and still get light to come out. And of course that is the one I've drawn right here. Right? This is any more shallow than this here, like any further this way, and it's going to get total internal reflection. So theta crit would be, well, sine theta 1 would be n2 over n1, would be the arc sine of n2 over n1. All right. That is when this is exactly equal to 1. And we already worked out what the critical angle of water is, for example. I think it was 48.6, something of the sort. I should actually double check that. Can't find my notes now. here we go. What do we, yeah, 48.6, right? That's what we worked out. That was the critical angle here. Of course, critical angle sort of assumes you're going the other way, like the fish was shooting here. But we worked out that that angle here, if this one's 90, and this one here is 48.6, any more shallow, and the laser ray will just bounce off and never actually leave the water. Okay. Point to emphasize, the critical angle depends not just are you in water, are you in glass, it depends on what is the other medium as well, right? So it depends on both media. Right, it's right here, N2 and N1. So glass in water is different than glass in air, for example. Alright, so does that have any uses? Yes, it does. So I'll say some applications. For example, it's used as reflection, say in binoculars, or a lot of other optical devices. So, for example, if this is here the binoculars, it looks sort of something like this, right? And you sort of look in here, and these are the lenses out here in the front. Then you might find that there's a sort of triangle of glass in here, and another triangle of glass, maybe sort of like this, and then the light ray would come in, bounce over, total internal reflection. You could put a mirror there, would have the same effect, but mirrors get dirty, right? The inside of a glass can't get dirty. And it goes out like this. And the same thing on the other side. And that much more sort of important application, I guess, nowadays is optical fiber. What's optical fiber? Optical fiber is something you couldn't really easily do with mirrors. I have some kind of long bendy tube, and it's simply made of glass or some kind of transparent glass-like medium. And then I can shoot light pulses down it from, say, here. I shoot some light, maybe some kind of, part of some electronic device. It shoots a light, and because the fiber is very narrow compared to the amount of bend, right? It's always going to hit the edge at a very fairly shallow angle and sort of bounce back and forth over really long distances. It'll never accidentally hit the wall at a too steep an angle and leave the fiber. And so you can send signals like along a sort of bendy fiber like that. And that's fiber optics. There are some other interesting applications too. For example, or application phenomena too, let's call it this way. For example, sort of mirage you see when it's a hot day, right? So, actually, let's see if I can find a picture of that. Here's a picture I just found with a quick web search. This is from Wikimedia Commons. So here you can see those cars, right? And then we see this reflection as if the road were wet, but it's not wet. It's just really, really, really hot. This sort of mirage, you can see, we don't get it much up here in the northwest, but if you go to maybe some desert states or midwestern states in the summer, you might find that. It gets really, really hot. The road heats up, right? The road gets really hot because of the sunlight. It's a black tarmac. It absorbs the sun rays. It gets really hot, and you know that when you put your bare foot on it. So what that does is that it heats up the air just above it. Right? So there's a layer of air just above the surface of the road that is really, really hot. Now, really hot air has essentially a slightly lower index of refraction than, colder air. So the rays move faster in it. So it's almost like there's the air that's everywhere, and then the air right above the road that is a different medium. In a sense, right? Because it's a different temperature. And so we get total internal reflection, where the internal part is just the air that's everywhere, more than a few centimeters above the road, and it bounces off the boundary between the cold air and a really hot layer of air just above the road. There's another picture I found. I'm just going to show this to you again from Wikimedia Commons, very basic, but it sort of gives you the idea, right? You see the car here, and then the light ray from the car that goes downwards bends because this layer right above the road is super, super hot. Right, so this is where the total internal reflection occurs. I don't know what these letters are. I just found this diagram online. And so it bends around. It's actually a sort of continuous process. It's like there's lots of layers of air of different temperatures. So it's not like once like a fixed boundary, but it happens gradually, like continuous refraction, continuous total internal reflection in a sense. So this light ray here, it bends because of the difference in the temperature up here versus just above the road. And that's why you see these sort of mirages. Okay, so in the end I just want to show you a little demo of this that I took in the physics storeroom. It's very dark, bit grim in there. And the video quality is a bit poor because I had to turn off all the lights because the lasers, and so not much light reached the camera. So accordingly the picture quality went down significantly, but you'll be able to see what's going on. So let me demonstrate refraction for you. With a laser pointer here, I'm going to shine that laser pointer through this water tank. I've added a little bit of milk powder to this tank to make the water a bit cloudy. What it means, the laser beam, when it falls through it, is going to scatter off these tiny little milk particles. That's where you can see it when you look at it from the side. So the first thing I'm going to do is I'm going to take this laser pointer, I'm going to shine it downwards onto the surface of the water. So you can see here's my laser pointer, it's pointing this way. When it hits this surface of the water, it's clearly bending downwards, right? Because it's not coming from up here, coming from over here. You can't see this part of the beam. There's no water there, nothing to scatter off, but then it goes down like this. It's the first observation, basic refraction. Now for the next part, I'm going to shine the laser into the tank from below. Well, I'm going to do it from the side here, but so that the beam will hit the surface of the water from below. See what I'm doing? I'm going to shining it like this. You can clearly see it in the water. And you notice part of the beam gets reflected here, another part appears over here. You can hopefully see it on my hand. So that the beam gets split up. And it hits the surface, it gets split up. The part that hits my hand over here, again, clearly has changed angle. Right? It's pretty steep up, then it goes this way and hits my hand over there. This beam here just gets reflected. Now, if I make the angle at which the beam hits the water more shallow, like this, again the reflection seems to become stronger, and indeed there's no point up here where the laser falls into my hand. So all the light gets reflected, and that means we found the critical angle, we've exceeded the critical angle of water relative to air.